is to show you how to set up the problem, the Colebrook problem in Matlab. What I have on the screen right now are the notes that I generated on my iPad while making the previous video. Recall that we're trying to solve this problem, and what we call the solution is going to be the value of f that satisfies the equation. So I want to perhaps do the first two parts of this problem. I want to put the Blasius formula as well as the Colebrook formula into a Matlab script, and then I want to plot what the root finding problem actually looks like, and I want to then try using MATLAB's fzero built-in function to actually calculate the value of f. There are going to be some wrinkles that you'll see shortly. Okay, so I'm going to start by creating a new script. So in MATLAB, a script is a file that defines a series of commands that just get run in order. I usually start my scripts with the commands clear, CLC, and close all. Clear erases the memory of any variables that may have been defined. CLC clears the MATLAB command window. And close all will close any figures that are open. So I'm going to start by defining my constants. So let's see if I can put this PDF file. So I'm going to define these constants. So I'm going to just type in the constants that are given to me. So rho is 1.23. So I like to define constants in the beginning just so I can type them once, I can check the numbers if I need to, and never type them again. Okay, now there's two ways of defining, let me save this file, there's two ways of defining functions. So I'm going to start with the more conventional way. So I'm going to say new function, and what this does is create a new .m file that gets saved into a separate file other than the script. And so I'll show you by writing a function that calculates the Reynolds number. So the Reynolds number is going to need density, viscosity, density, velocity. It's this equation right here. Diameter and viscosity. And it's just density times, actually the output I'm going to call RE, and RE equals density times velocity times diameter divided by viscosity. Okay, so let's attempt to use this. So if I say Reynolds number in my script, and I send it rho, v, d, and mu, then it should calculate the Reynolds number based on the values of those variables. In this case, our Reynolds number is something like 13 or 14,000. Okay, so I don't actually need this. I'll comment it out for the moment. It just shows you how I can define a Matlab function. So there's another way that's very convenient in problems like this, another way of defining functions. So I'm going to use this method, it's called anonymous functions, to define the Blasius equation. So I'm going to say Blasius f equals at density, velocity, diameter, and viscosity. Okay, so I'm defining my function in the script. This at symbol and parentheses defines the inputs to that function. And now if it's a simple one-line function, I can define it in the script itself. So what I've typed here is this, the formula for the friction factor as predicted by the Blasius formula. So 0.316 times the Reynolds number to the power 0.25. So that's here. Reynolds number is actually calling a function, so you have to send it the information it needs. And now let's use this to see if our guess for the Blasius, I'm going to take the semicolon. Oh no, I'm not going to take it off of here. I'm going to call it. So I'm going to say Blasius f equals, actually I'm going to say f0. That's my initial guess. Let me go back. So my initial guess for the friction factor f0 is going to be the Blasius formula. So that's going to need rho for the density, v for the velocity, d for the diameter, and mu for the viscosity. So let's see if that works. Okay, so there you go. It calculated an initial guess for mu. So the nice thing about anonymous functions is that they tend to be more compatible with simple mathematical formulas, because a simple mathematical formula can define the function output in a single line. So you don't have to actually look up code in a separate M file in order to know what is going on. So the other thing I'm going to show you later is that anonymous functions make it handy to plug in values, right? So say you want to define a function based on the Blasius function, in which you plug in most of the numbers here, but you keep one as a variable. That can be done fairly easily using anonymous functions. So I'll show you something like that soon. So now I want to use the Colebrook formula. So you may have noticed that we completed part A of this problem. We calculated initial guess f0. Part B of the problem is asking us to use the Colebrook formula and f0 to compute a solution. The problem doesn't actually ask us to make a plot, but I'm going to actually make a plot before I do it of the Colebrook problem. So let's make an anonymous function. let's see, what other friction factor? So these are all the variables that show up here in the Colebrook formula. And I am now going to enter, so remember, we're going to solve this as a root finding problem, so I'm going to have 1 over square root of f, and then I'm going to move this to the other side, to the left side of the equation, so it's 1 over square root of f plus 2 log of this stuff. Okay, so I'm going to say, and if you don't know what the dot slash means, don't worry about it, just ignore it for the moment. If you do know what it means, you'll know that I'm trying to vectorize the function. So 1 over square root of the friction factor plus 2 times log 10 of the roughness divided by 3.7 times the diameter plus 2.51 divided by Reynolds number density okay, and then then the square root of the friction factor. Okay, so assuming I type that in right, so again, I'm just typing this plus 2 times the log of that in order to create a function that should be 0 when the friction factor is correct. So watch this. So now this, I'm going to do that trick about plugging things in. So I'm going to say to solve, the function I want to solve, is an anonymous function of x, and I'm going to say so I have values for everything except for the friction factor. So I'm going to say rho, v, d, mu, epsilon, and x. So now this function to solve is a single variable function defined by the Colebrook equation and then plugging in all the constants that I know. Okay, so let's try running this. I'm going to try running this by sending or calculating to solve, and I'm just going to send it f0 as x. Let's see if I typed anything wrong. Okay, so looks like I forgot an n over here. More problems. Roughness. Undefined function of variable roughness. Oh, I forgot an n. I actually didn't forget. It just turns out that my computer has a bad n key. Sometimes when I hit n, it doesn't register. Okay, so when I send it f0, now the code does not give me an error. I'm going to put a semicolon here just so it suppresses the text where it defines the function. And I don't know if this is right or wrong, but now let's do something. So, well, actually, I do know that it's wrong. So when I send f0 to solve, I don't get 0. If this was correct, then I would get 0. So let's actually try plotting. So I'm going to use fplot. I'm going to plot toSolve. And I'm going to give it a range -5 f naught to f5 f naught. So I'm just guessing a range of x values to plot so that I can see if my function crosses the x-axis. Do I have a plot? No, I guess it's still working. Okay, so, well, I do not quite have, so the plot, it's high and comes down. Maybe if I go further, I'll get it to cross 0. So let's actually, I'm going to plot from 0.1. And let's see, how far should I go? It's on its way down, so let me go to 5. Okay, so it looks like we are crossing 0. So we're crossing 0. We can use this feature. To see where it crosses 0. It looks like it crosses 0 at about 0.2. Right, I guess it's not that easy to tell, but see here, there's a sign change over here, and this is at about 0.2, right? So notice the Blasius guess was way off. It's actually more like 0.02. So let's use Matlab's built-in fzero. We're going to start with the guess of fzero, which looks like it's, from the plot, it looks like it's pretty far off of the right answer, but let's see if fzero can find the answer. And, oh, whoops, fzero needs to know the function, so okay, so looks like fzero has failed. So I actually knew this ahead of time because I have done this problem before. So when I guess the Blasius guess for toSolve, it tells me that fzero has failed. And by the way, NaN means not a number. But I think we can do better in terms of the guess because we have the plot. So that's a good tip. It's good to plot things if you can, and they help you set up your problems well. So if I guess 0.2, let's see if fzero is able to get me my answer. Well, there you go. So I'm going to say correct f, and I'm going to now plug in toSolve using the correct f. And in fact, it gives me 0 when I plug in 0.2108. So in fact, that's the right answer. But the twist I mentioned in the beginning of the video is that the problem, as stated, tells you to use the Blasius guess fzero as the initial guess, but it actually fails. So the Matlab function fzero does not get the answer with that guess. And by the way, this is a common occurrence in numerical methods. Even if you give it a good guess, sometimes methods fail. So this was intentional on my part. I knew this was going to happen. In the next video, I don't want to rely on fzero. But instead, I want to actually talk about how to use our own implementation of Newton's method to actually solve the root finding problem.